Assalamualaikum. It's our 15th lecture of Principal Methods and Applications of Nuclear Tracks, and in this lecture, we are going to discuss chapter number 7 of the book James E. Tuner, and the chapter is Phenomena Associated with Charge Particle Tracks. Okay, so in this we are discussing about the phenomena, phenomenon which are associated with the charge particles and the tracks that associated with the charge particles. So first of all, we have to discuss about the delta ray. What is basically the delta rays are? Basically, the delta rays are heavy charge particles. Okay, or an electron, you can say, when they are transversing means they are traveling. Okay, when those electrons or charge particle transversing matter sometimes produces a secondary electrons. Okay, so let's suppose you have a nucleus. Okay, you have a nucleus, you can see you have a nucleus, this, and here you have an electron, some charge particle, or you can say photon, is coming, and this and have enough amount of energy to eject that electron. So this electron ejected from its outermost shell and ejects, and let's suppose there is another nucleus. Okay, and it has again an electron. So the ejected electron also ejects the another nucleus electron. So this process is called as the delta rays. Okay, and this first ejection of electron is known as primary ionization, and this second ejection of electron is known as the secondary ionization. Okay, so here you can define it as a heavy charge particle or an electron transversing matter sometimes produces a secondary electron, which I told you. Okay, it produces a secondary electron with enough energy. Okay, you can say with enough energy to leave immediately vacancy of the particle, because once this electron is ejected, there is a vacancy. Okay, of primary particle, and produces a noticeable track. Definitely, when your electron is removing from their shell, there is a vacancy and there is a noticeable track formed. You can easily discover the track formed by this primary and secondary ionizations. Okay, such a secondary ionization is known as the delta rays. Okay, such a secondary ionization in which your primary ionization ejects an electron and makes a noticeable track. This process is known as delta rays. Okay, so we can also illustrate this in figure 7.11. We can discuss this. Here you can see this is for proton and this is for alpha particles. Here you can see there is less energy and there is more energy. You can easily discuss from these graphs is as the energy increases, you can conclude that the track thickness in low. Okay, so as the amount of energy increases, the track thickness gets low. You can easily illustrate this from the graphs, and this lines basically showing us here is basically the secondary ionization. These excluded lines basically showing here is the secondary ionization formed here, these lines, and this straight path basically showing the primary ionization. These lines you can see showing the secondary ionization. Okay, these lines, and you can easily see as the energy increases, the thickness becomes low. Okay, so that's for the delta rays. Now, as for the 20 mega electron volts alpha particle produce the very high energetic delta 1. Okay, as I told you, as the amount of energy increases, let's assume you have an amount of energy 20 mega electron volts alpha particle. Okay, and this is the and this range of energy of an alpha particle basically produces very high energy delta rays. So when very high energy delta is formed at 2 at 20 mega electron volt alpha particle. Okay, if the alpha particle got an energy of 20 mega electron volts, then the primary secondary ionization formed due to delta rays is basically very high energetic delta rays, which itself produces another delta ray. Definitely we know that when one delta ray form, they can also produce another delta ray, because there is a continuous process. Okay, there is no sharp distinction in how to distinguish one secondary electron along the track as the delta ray and another exhibit. Okay, so its track can be noticeable, so we can easily noticeable the tracks or distant from that of primary charge particles. Okay, and the tracks of secondary must be different from the primary, as I told you from figure 7.1. Okay, so this is all about the delta rays. Now move on towards the restricted stopping power. We already discussed what is stopping power in our previous lectures of principal matters and applications of nuclear tracks. We have a detailed lecture on stopping power. You can watch those videos first. So what is basically the stopping power? Stopping power is basically the uh, decrease in energy. Okay, you already know that this is basically the rate of energy transfer. Okay, stopping power is basically the rate of energy transfer with respect to distance x. Okay, and there is a decrease in energy. That's why we call there is a negative sign in the formula of the stopping power. So basically, the how we can define the radiation dose. Basically, radiation dose is defined as the energy absorbed per unit mass in an irradiated material. Definitely, so the energy absorbed per unit mass of an irradiated material. This is basically called as the radiation dose. Okay, and absorbed energy thus plays a preeminent role in the dosimetry and in radiation protection. Okay, so what is basically the stopping power? As I told you that the stopping power basically gives the energy lost per a charged particle in the medium. So if there is an energy lost in some medium by any charged particle, so there is a stopping power medium is concerned. So this is not only always be equals to the energy absorbed in the target, especially if the target is small. Okay, so if the target is small, this is no always equals to the energy absorbed in the target. Understood? And if the target is small as compared to the range of the secondary electron produced, understood? So here you can see the dimension here is given for, let's suppose, our DNA double helix, for example, has a diameter of 20 angstrom. Okay, 10 is to power minus 10, and this is equals to 10 is at 20 multiplied 10 is to power minus 8 centimeters. Okay, so delta rays and other secondary electrons can effectively transport energy out of the original site in which it is lost by a primary particle. So the concept of restricted stopping power has been introduced to associate energy loss in target more closely with the energy. So you have an energy and there is some amount of what energy loss in a target which is more closely with the energy that is actually absorbed there. Understood? This process is basically the restricted stopping power. And the restricted stopping power, as I mentioned before, is denoted by this minus dE by dx, because there is a rate of loss of energy with respect to distance, and delta sign for the restricted stopping power. So we can define the restricted stopping power as a linear rate of energy loss. Because there is a linear rate of energy loss, then we can say that this is restricted. If there is no linear rate of energy loss, then this is some other stopping power. For the case of restricted energy loss, the energy loss should be linear. Okay, only to the collision in which the energy transfer does not exceed a specified value of delta. Okay, means changing. So how you can calculate the restricted energy loss, restricted stopping power? To calculate this quantity, one integrate the weight energy loss. So we have to basically integrate the weight energy loss spectrum. Okay, which is this Q max, which is this delta, and rather than Q max, in this here you can say we have to integrate from Q minimum to delta. In original formula, here is Q minimum to Q maximum, but in restricted energy loss, here is from Q minimum to delta. So you have to integrate the weight energy, which is this, and you will get the stopping power. Here is a factor which is mu, and this mu is basically the attenuation coefficient. You already know what is the attenuation coefficient. So this is basically the formula for the uh, restricted energy stopping power. Understood? Now move on towards the next, which is this, which is all depending upon the applications. You can also define minus dE by dx like this. It also goes to infinity, and these is some examples. Understood? Here is a table you can see, which is the restricted mass stopping power of water. Okay, in mega electron volts per centimeter square per gram for proton. This is at 100 eV. This is at 1 kilo electron volt. This is at 10 kilo electron volts, and this is for infinite range. So at these energies in mega electron volts, the stopping power is mentioned, is illustrated in this table. Okay, and this is table 7.2 for the restricted collisional mass stopping power of water. Okay, same procedure energies in mega electron volts for 100 ev, 1 kilo electron volts, 10 kilo electron volts, and infinite range. Understood? Now move on towards our last topic of this lecture, which is the LET, which is so called as the linear energy transfer. What is linear energy transfer? Basically, linear energy transfer is basically the rate of energy transfer per unit distance. Understood? This is again the same as the restricted energy loss, which is the rate of energy transfer per unit distance, and LET is also same, the uh, energy release, or you can say the rate of energy transfer per unit distance. Okay, so the concept of linear transfer, or it is denoted by LET, was introduced in early 1950s. Okay, to characterize the rate of energy transfer per unit distance, which I told you. Okay, this is the definition of the linear energy transfer. In this, your again the parameter is linear. Okay, if there is no linear parameter, then there is no LET. Okay, so in LET is concerned, only your rate of energy loss, rate of energy transfer per unit distance along a linear path, you can say along a charged particle track. Okay, such as LET as stopping power was synonymous in studies radiation effect. In term of LET, the distinction was made between the energy transfer from a charged particle in a target and the energy actually absorbed there. Okay, in 1962, the International Commission on Radiation Unit, this is basically ICRU, okay, Commission on Radiation Unit Measurements, ICRU, defined LET. How they define LET? Because you know that many measurements they define their parameters. So LET can be defined as a quotient of minus dE by dx. Only there is an L in the subscript. So basically, the LET is similar to the restricted stopping power, which is rate of energy transfer. Okay, where DEL is the average energy locally imparted to a medium by a charged particle. Okay, in traveling a distance, a specified distance, traveling a specified distance dx, the word locally imparted, however, not precisely specified. The LET not always used but exactly the same measuring in 1980. Okay, the ICRU defined, now ICRU how defined LET as mentioned here, that the formula they defined as the restricted stopping power for the energy loss not exceeding delta. Okay, so the formula for the LET delta is same as the restricted stopping power for the energy loss not exceeding delta. Delta, which is the change, the value is not must be exceeded delta, and the formula of LET remains same, which is minus dE by dx. Okay, which you can find by this formula. Okay, so here again, if you have a problem, you just have to multiply. So here is an example you can see using table 7.1 to determine LET 1 keV, LET 5 keV, and for 1 mega electron volt proton in water. So this is a problem. we have to solve this problem. How we can solve? Note that equation 7.3, which is this I mentioned, this is equation 7.3, and for LED involves stopping power rather than mass stopping power. For water, you know that the density is 1. Okay, and the Numerius number in table 7.1 gives, you know that the LED formula is this: in mega electron volts mega electron volts centi per meter per centimeter. We can find LED 1, which is 238 mega electron volts. You can see from figure LED 1, you can from this graph here you can see LED 1, which is here. What's the value? Basically LED 1 kilo electron was 238. You can see LED 1 kilo electron was 238. 1 kilo electron was here. So if the energy is 1, so you can see it's 238 in 1 kilo electron volts for water. Understood? For water. Similarly, you can see here 238, not here. Okay. So for 1 mega electron volt, okay, so energy is 1 mega electron volt proton in water. So you can see if proton in water, 1 mega electron volt energy is 238. Understood? Similarly, you can see for uh, others. Okay, given directly in table you can see, and because they are also saying that to find LT 5 kilo electron for LT for 5 kilo electron for 1 EV energy for proton in water. So let's check the table. So this is our table for 5 kilo electron volts we have or not. For LED 5 kilo electron. Okay, so let's check. Here we have 1, here we have 10, we don't have the value. Here is 270, so here is 238, we need in between value. Basically what we have to do here, because we are finding the value of 1 kilo electron volt for this, but we don't have for 5 keV. Here we have 10 keV, we need intermediate value. So what we have to take average, sum of this plus this divided by 2, so we get the value at 5 keV. And after calculating, so what we have to do, we have to do 238 plus 270, okay, divided by 2, because this is 1 and this is 10, in between divided by 2, half of this is 5, okay, and that's why I'm dividing by 2, so we are getting 252. Okay, so this must be the value. Let's check. Uh, yes, we are right. So LET 5 keV value is 252 mega electron volts per centimeter. So this is basically how you can find the linear energy transfer. Okay, so linear energy transfer can also be expressed in kilo electron volts mu per meter mu, which is the attenuation coefficient. Okay, and that one kilo electron volt mu per meter basically equals to 10 mega electron volt per centimeter. Understood? This is a very good conversion. You can say how 1 kilo electron volts mu per meter equals to 10 mega electron volts per centimeter. This is a conversion. Okay, so that's all for today. We discuss about the our chapter number 7 of the book James E. Tuner, in which we have started chapter number 7, phenomena associated with charge particle tracks, and we discussed about the delta rays. And in delta rays we discuss about the produces noticeable tracks, and we discuss about the primary and secondary ionization. We discuss how alpha particles at 20 mega electron volts energy produces the very high delta rays. We also distinguish between the primary and secondary tracks, so that we cannot distinguish between the primary and secondary tracks directly. Okay, we also visualize that as more energy tracks thickness becomes low. Okay, we discuss from these graphs. And next we move on towards the restricted stopping power, in which we discuss about the radiation dose, which is basically the energy absorbed per unit mass by some irradiated material. And we discuss their formula for the radius restricted stopping power. And then we move on towards the LET, which is the linear energy transfer. Okay, and we did a problem related to LET and restricted stopping power. So that's all for today's lecture number 14 for principal matters and applications of nuclear tracks. And we will upload more interesting videos for this course. Till then, take care with, okay, and stay tuned with us. Allah Hafiz.